So here are the final results. These are the terms with p-values less than 0.05. So we conclude that these are the vital x's. The effect column measures the overall effect on the y of moving from the low, or -1 level, to the high, or +1 level. In the case of the application type, for example, the effect of moving from a paper form to an electronic one will reduce the number of missing data fields. Likewise, the effect of flagging each required data field will also reduce the number of missing fields. We will now build an equation to predict the number of missing data fields we can expect as a result of implementing these two changes. We start with the constant coefficient. We then add to that the product of the application type coefficient and the assigned value of the type we will implement. In this case, the paper application is -1 and the electronic form is +1, so we will use +1. In a similar manner, we add to that the product of the field highlighting coefficient and the assigned value of highlighting the assigned fields, which is also +1. Finally, we add the product of the coefficient of the interaction of the application type and field highlighting, which means changing simultaneously from the paper form to the electronic one, and from no required field flagging to the use of required field flagging, and the product of the assigned value of each. By taking all the products first, we simplify the equation to this straightforward string of additions and subtractions, which adds up to 4.25 missing data fields, which looks like it will meet our requirements as estimated earlier. Click Next to continue. Be cautious when using the preliminary transfer function with continuous data. It is limited in that it will not reveal any curvature. We use it to help identify a vital x, but not to optimize the actual setting. When you have such a situation, you can use optimization DOE or other tools to optimize the setting of a vital x. Click Next to continue. Another thing we can now do is generate a graphical representation of the actual factorial screening. This often provides visually dramatic results. However, graphical representations must always be backed by statistical results. From the Stat menu, select DOE, and then Factorial Plots. When you select Factorial Plots, the following dialog screen will appear. We will use the default of data means for our plots, so no change is needed for that factor. There are 3 kinds of plots that you can do. Since we have already limited our scope of interest to 2 factors, we'll click on the first 2 buttons. Upon selecting a plot, the Setup buttons become active. So let's click on the top Setup button. When you click on Setup, Minitab displays the following dialog box. Let's go through the proper setup. First, we need to select a response. This is the y we believe our vital x's will influence. The response value is the number of missing data fields in column C8, so we place our cursor in the Responses field and click on C8. And then click on the Select button on the lower left. You could also double-click on an item, which will perform the same function as selecting the item first and then clicking on Select. After successfully entering our response, we look at which factors to include in the plots. Our 3 factors are in the Available box. We are not interested in the font size, so we will select the application type and field highlight items and click on the top arrow to transfer each to the selected window. This screen shows all proper choices selected. When you press OK, you will return to the Factorial Plot main menu. From this screen, check the settings for the other plot by clicking on the second Setup button. Make certain that both have the same factors defined. Once you have completed the setup, click on OK to execute the plot. Click Next and we'll start looking at the data. This first graph shows us the individual factors plotted against the number of missing data fields. The height of the line demonstrates the impact of the change. It appears that there is a sizable decrease in the number of missing data fields when we switch from paper to electronic applications. It also appears that there is a similar decrease in the number of missing data fields when we highlight the required data fields. For additional information on screening design analysis, click on Tell Me More. So here in Step 7, our primary task was to identify the vital X's for our Y. We also looked at a strategy for determining our exact improvement plan. We reviewed the applicability of using a design of experiments approach to this process and executed a full factorial screening DOE. As part of the design or screening experiment, we took steps to limit the possible effects of any lurking variables. So now let's see how this applies to the commercial loan case. Click Next to continue. So we designed and executed a full factorial screening on our 3 potential vital X's. We used replication and randomization to enhance the reliability and credibility of our experimental results. We have determined that the application type, required field highlighting, and the interaction between application type and required field highlighting are significant factors. But the font size was not. Since the 2 vital X's are both discrete data items, there will be no need for further experiments in order to set the values. We will, however, explore techniques which may be required when dealing with continuous data in the next step. So we're about ready to wrap up this section of the course and the case, and move forward to the next step of the Improve phase. Click Next to continue. Well, that wraps up Step 7. Congratulations! We have correctly identified 2 vital X's which we will optimize in the next stage to lead us to the fulfillment of our process objectives. You can either click on Next or stop at this point. In Step 7, we narrowed the vital X's down to 2. Due to the fact that they were both discrete items with only 2 possible levels, we also determined what our changes would be. That is not always the case. When you have a vital X which has multiple levels, you will need to run additional experiments in order to determine the exact changes required. In this short section, we will discuss some of those possibilities. Click Next and we'll begin. Let's look at the learning objectives for this step. When you finish Step 8, you will be able to perform optimizing experiments in order to develop the Step 8 deliverable, which is the proposed solution. Describe considerations and potential trade-offs involved in reducing the number of experiments. Click Next to continue. Once you know what you are going to change, you can narrow your focus to determine what the precise changes will be. Now let's discuss some issues which may impact your experimental design. While exhaustive testing may be desirable, budgetary considerations may require you to reduce the number of experiments. There are statistical approaches such as the fractional factorial design which can assist you in this task. It will take a certain number of person-hours to run each experiment. This may be another limiting factor. In certain situations, a solution must be implemented in a timely fashion or the project objectives will not be met. Your experimental design must take this into account. Depending on your process, there may be a number of other resources which can limit your experimental design. You will have to accommodate them when you reach this stage of the project. As discussed earlier, the full factorial test may require a large number of runs as the number of factors and levels increase. If you need to reduce the number of experiments, you can use a fractional factorial design, which involves selecting and testing an appropriate subset of all possible combinations of factors. This design may also be applicable in the screening process of Step 7 as well. A trade-off in using only a subset of possible combinations is that we will lose some information about the interactions among factors. Techniques and tools to aid you in selecting the appropriate design will also be covered in further training. Click Next to continue. The analysis of data gathered from an optimization experiment is the same as the analysis of data gathered from a screening experiment. You look for factors which have a p-value of less than 0.05. Those factors are then placed into the prediction equation, and the equation is solved to provide the optimum result. Due to the fact we had only discrete factors, we did not have to run a separate optimization experiment. We have established that a reduction in missing data fields is directly connected to a reduction in data entry cycle time, and the predictive equation quantifies that relationship. By setting y for our target time of 48 hours and solving the equation for x, we discover that our average x should be no more than 4.43 missing data fields per application in order to meet our target. Click Next to continue. So the summary of Step 8 is that we accept the vital x's identified in Step 7 and, where necessary, determine what actual changes in those vital x's are necessary to meet our project objectives. Click Next to continue. Because our vital x's were simple discrete variables with only two possible levels, the kind of optimization DOE normally done in this step was not required. We already know what the changes will be. So our recommended solution to address the data entry cycle time is to reduce the missing data fields by switching over to all electronic forms and flagging or highlighting the required data fields in the data entry system. We're almost done with the improve phase. There's only one more topic to examine, and that is the use of statistical tolerancing when necessary.